Okay, now we're going to look at statistical inference. So let's start with example 16. Kissing couples lean their heads either to the right or to the left. Do they lean their heads to the right more often than to the left? After all, most people are right-handed, and for most people, the right eye is dominant. Scientists have suggested that late-stage human embryos even turn their heads to the right in the womb. Perhaps this right tendency is reflected in how couples kiss as well. But by studying a sample, even a random sample, you expect the sample proportion who lean right may not exactly reflect the population proportion, but how much do they differ? I mean, for example, if 65% of couples in a sample lean their heads to their right, does that guarantee that more than half the population leans to the right? Now, we've discovered in previous topics that although there is variance, the variation has predictable patterns, and if we have a large enough sample size, the pattern follows a normal distribution. Therefore, we can calculate probabilities of different outcomes using the appropriate normal model. In this topic, you will continue to practice with these calculations while looking ahead to ideas of statistical inference that we'll be getting into in later chapters. Now, I meant to fix some of this because this notation wasn't exactly what we've been using, so if you want to change it with me. If we're talking about proportions, the sample statistic is P with a little hat on it. The center for the population would actually be a P. I don't know why it has a pi there. And the standard deviation would be the square root of P times 1 minus P divided by N. And we assume it's approximately normal. And we need to know that N times P or N times the opposite had to be greater than 10. Now with means, we have the sample mean, the population mean, our formula for standard deviation, and we know that it's either normal if we know the population is normal, or it's approximately normal if our sample size is large enough. We determine statistical significance of a sample statistic by exploring the sample distribution of that statistic, investigating how often an observed sample result occurs simply by random chance. Roughly speaking, a sample result is said to be statistically significant if it is unlikely to occur due to random sampling alone. We will also discuss statistical confidence. Although you cannot use a sample statistic to determine a population parameter exactly, you can be reasonably confident that the sample statistic falls within a certain distance of the population parameter. Therefore, once you observe the value of a sample statistic, you can be confident that the population parameter is within that distance of the sample statistic. Now, a common error when working with the central limit theorem is to forget to incorporate the sample size into the standard deviation of the sample mean. Don't worry about the shape of the population distribution when the sample size is large. Because remember, if it's over 30, then you don't have to worry about anything. Okay. Assuming the appropriate conditions are met for the sample distribution to be approximately normal, the distribution for a sample proportion is approximately a standard normal distribution. And here's some formulas, but we really don't need to use these formulas so much because we can use the calculator to calculate. So to get those z-scores. So let's say we have a simple random sample of size n equals 49. Simple random sample. So it's a random sample. We need that. It's obtained from a population with a population mean of 80 and a standard deviation of 14. Describe the sampling distribution of x bar. So even though we don't know that the population is normal, n is greater than 30. So That means the shape is normal. The center, X bar, would be the same as our population mean, so it's 80. And our standard deviation, our spread would follow the standard deviation formula. Take the standard deviation of the population divided by the square root of n. So 14 divided by the square root of 49, well, that's easy, that's a 7, that's just a 2. Now, what is the probability that a mean from a sample is going to be less than 75.8? Well, let's think about what this distribution would look like. The mean is 80, and our standard deviation is 2. So 1, 2, 3, 1, 2, 3, 82, 84, 86, 78, 76, 74. Probability of being less than or equal to 75.8. That'd be just this little tail, wouldn't it? So, CDF. The lower boundary would be negative 1 times 10 to the 99th power, so negative infinity to 75.8. The center is 80, standard deviation was 2, and it gives me 0.179. 179, I forgot the 1. What about between 78.3, let's get a different color, be about here, and 85? Ooh, this should be a much larger probability, right? So normal CDF, because we're between two values, 78.3 and 85.1. Nothing else has changed, and that's 0.797 basically. Now, I said let's not worry about those formulas, but I don't remember if I signed any homework that had it. So let's. I'm going to backtrack on my own statement, and let's find the standardized statistic for the sample proportion. In other words, using that formula from up there. It says to take the p hat minus p over the standard deviation, which would be the square root of p times 1 minus p over n. Well, this is saying that p hat, so the sample proportion is 0.60. The population proportion is 0.50. And in here, we're going to be taking the values from the population. So this would be 0.50 times 1 minus that, which would be 0.50, divided by the sample size of 100. Now, I'm going to do this as a fraction in my calculator. 0.60 minus 0.50 over the square root of, and put another fraction in there, 0.5 times 0.5 divided by 100. And we get 2. That's a z-score of 2. So remember, that's 2 standard deviations to the right of the center. What if we change that to a 200 for the n? So I can actually copy and paste that and go in and change that to be a 2. And it's now a z-score of 2.82. 28. And then there's a formula also if you needed to do that for the sample mean. Alright, but what we mainly want to do is solve problems with this. So a blind taste test is done to compare COLA 1 and COLA 2 among a sample of 75 participants. the proportion is 0.64 that prefer color 1. If actually the two colors are equally preferred in the population, 0.5, that would be the population proportion. Assuming that the population proportion is 0.5, find the following. So on the first one, we're going to find the probability that our sample proportion is greater than 0.64. So first off, we got a couple of things to take care of. We got to meet our conditions. So n times p has to be greater than or equal to 10. So 75 times 0.5 would be, it's half of that, so it'd be 30 something. Yes, that's good. N times p minus 1, 1 minus p, I backward, would be 75 times, again, 0.5, because half and half. That'd be good. Now I need to know the standard deviation that I'm going to be using. Well, reminder that on proportions, the standard deviation is going to be the population proportion times 1 minus the population proportion divided by n. So, square root of, and you can make it a fraction if you want, 0.5 times 1 minus 0.5 divided by n is 75. Oh, I know why it said error, huh? I forgot to put 0.5 here. It makes a big difference. So I get standard deviation of 0.0577. So that's the standard deviation of my samples. Now, being greater than 6.4, so remember the middle is 0.5, so being greater than 6.4 is going to be pretty far off. .64 to 1E99, the population mean 0.0577. I get 0.0076. What is the probability that the proportion is less than 60? Okay. Think about where that would be. 0.5 is here, so less than 0.6 would be a pretty big area. So we're going to go back in, normal CDF, negative 1e to the 99th power. The upper boundary is 0.6, nothing else is changing. 0.958, so there's a very strong probability that it's actually less than 60%. Assume that cans of Dr. Pepper are filled so that the actual amounts have a mean of 12. That actual amounts tells me that's the population. So that's telling me the population mean is 12 with a population standard deviation of 1.5. Find the probability that a sample of 36 cans, samples larger than 30, yay, will have a mean amount at least 12.35. So we want to find the probability that X bar is at least 12.35. Okay, I need my standard deviation of the sample. That's going to be 1.5 divided by the square root of my sample size. So sample 36. 1.5 divided by the square root of 36, that is 0.25. Greater than 12.35, 12.35 would be my lower boundary. The mean is going to be 12, but we're using the standard deviation of the sample distribution. And I get 0.08. Based on tests of the Chevy Cobalt, engineers have found that the miles per gallon in highway driving are normally distributed. Woo! With a mean of 32 and a standard deviation of 3.5. Wonderful. What is the probability that a randomly selected cobalt gets more than 34? Now we're talking about just randomly selected over the population. So this is a population question. The probability that a randomly selected cobalt is greater than 34. We're going to be using the population information for this. So 34, the mean is 32, and the standard deviation of the population is 3.5, and I get 0.28 approximately. Now, 10 cobalts are randomly selected, and the miles per gallon for each car are recorded. What's the probability of the mean miles, exceeding 34? Now, here's where we're going to take into consideration that this is talking about samples. So the mean that we'll be using is going to still be 32, but the standard deviation is going to change. It's going to be 3.5 divided by the square root of the sample size. Now you say that sample size is too small. They told us it was normally distributed. So if we know the population is normal, then the sample size does not matter. Whoops, I forgot the divide by sign. 1.107 is the standard deviation. So I'm going to change that standard deviation. 1.107. So when we're talking about the sample distribution of the means, that is different than talking about the population. Now let's say we change it to 20 cobalts. That changes my standard deviation. And that gives me 0.783. And again, we want to know the probability of the mean of a sample being greater than 34. So the only thing that's going to change is my standard deviation. Notice the standard deviation is getting smaller and smaller and smaller. And that is actually making my probability get smaller and smaller and smaller. Now the last thing I want to add to this is something I should have added as an example. Just to kind of review something. So from the population, it's going back to just population information, find the miles per gallon for a car in the top 10%. So let's think about what that would mean. Okay, here's my sample. 32's here. Top 10%. Ooh, be 0.10 right there. For this we use inverse norm. Now, in my calculator, it does allow me to put that I'm shading the tail on the right. So 0.10, we're talking about the population. So the population standard deviation was 3.5, and I'm talking about the 10% to the right. That would be 36.48 miles per gallon. So that was just reviewing how to use the inverse norm to find values.